Vector functions and space curves. In this video, we're going to do some drawing. We're going to talk a little bit about what's called a vector valued function. And we're going to use our previous knowledge from this course to help us do these problems. Consider r of t, which equals a vector f of t, g of t, comma h of t, which is called a vector valued function. Notice that we have one input, which is t, and in this case we have three outputs, f, g, and h, or x, y, and z. So this shape would be a one-dimensional surface, or one-dimensional curve, I should say, snaking through three-dimensional space. Throughout this chapter, or this unit on vector functions and space curves, we can use the rules we learned in algebra about domains and a bunch of other things, as well as calculus like limits and derivatives and integrals, because all those rules are still applicable here. So instead of going through all the rules, let's draw or describe a couple graphs of these vector valued functions. Consider r of t equals 1 plus t, comma 2 plus 5t, comma negative 1 plus 6t. Hopefully you recognize this as a line in three-dimensional space that has what I would consider a starting point. That's my term. A line, of course, doesn't really start. But at least I know that my line goes to the point 1, 2, negative 1. And it's also parallel to the vector v, which is a vector 1, comma 5, comma 6. So I'm going to describe this instead of drawing it. We have a line through the point P naught, which is parallel to the vector v. If you need to review lines in 3D space, just go quickly watch that video to remind yourself. But let's draw a picture now. Consider r of t equals cosine of ti plus sine of tj plus tk. Or cosine t sine t t. What does this shape look like? Let's take the idea sort of a trace and sort of a projection. That is, let's just look at the cosine of t, sine of t part of the vector. Let's just look at that part. So if we have x equals cosine and y equals sine, I know that x squared plus y squared equals 1. So I'm not worried about my height, if you would, which is t, or the z part is t. I'm just looking about and concerning myself with this part. So if we were strictly in the xy plane, we would have a circle with radius 1 centered about the origin. Now, let's consider our height z equals t. So it doesn't matter our height. If we're looking at the projection from above the z-axis, and remember that I think of a projection as being like the shadow cast by a light, that is a light, not an eyelash, above the xy plane, it doesn't matter my height. The projection will always look like a circle in the xy plane. Meaning it doesn't matter how high I go up the z-axis. When I'm looking from above, I would always get a circle with radius 1 centered about the z-axis. So this is not my shape, but this is going to help guide my shape because I have one input and three outputs. So I know I have some sort of one-dimensional curve. But I drew this because what it's going to turn out is that my shape is going to wrap around this curve. For example, when z equals 0, when you're in the xy plane, we do get the vector cosine t, actually cosine of 0, sine of 0, comma 0. So when t equals 0, we get that vector. So that's the point, or the vector, 1, 0, 0. So I have a starting point right there. And then I have this circular pattern because I know the projection is always going to give me a circle. But I also know that t increases means that my shape is going to get higher and higher around these circles that are traveling up this cylinder. And so we end up with this sort of shape. We end up with like a coil that is wrapping around our cylinder that's getting higher and higher as t increases, because as the t increases, remember, t over here is also my height, z. How about this next one? Let's go back to lines to give it a little more practice. Find an equation for r of t if we have a line passing through the point 1, 3, negative 2, and another point 2, negative 1, 3. So I'm going to use this as my starting point, or the point on the line. And then I need a vector parallel to the line, which of course, PQ being on the line will be parallel to the line. So my vector PQ will be the vector 1, negative 4, and 5. Which means the equation of my line in vector form, or parameterized form, would be my starting x plus slope times t in the x direction, then my starting y, and then minus 4 times t, because negative 4 is like the slope in the y direction, and then my starting z plus 5 times t in the z direction. Let's do something a little more complicated, or at least appears complicated. Let's find a vector-valued function for the intersection of the cylinder x squared plus y squared equals 1 and the plane y plus z equals 2. Now, the intersection is going to be at a slant. But again, let's look at our projection as if we had a light shining directly down the z-axis. And notice that the intersection part would still be a circle, that is, the projection of the intersection part into my xy plane would be the circle onto the xy plane is the circle x squared plus y squared equals 1. So even though the intersection is slanting, when I look straight down above and just looked at like the shadow cast into the xy plane, I would see the circle x squared plus y squared equals 1. So let's parameterize the circle. That is, let's parameterize this part of it. Well, anytime I see this, my go-to is cosine t sine of t. It's not the only way to parameterize it, it is the standard way, and all I need is a way that works. So if I'm going to let xy equal cosine of t sine of t, I have 2/3 of my r of t, which is going to be x, or what I called f of t above, and then sine, called g of t above. And the only thing I'm missing is the z part, or the h of t. Well, let's look at the other equation, which is y plus z equals 2, but I already chose y to equal sine of t. So I could substitute it in and get sine t plus z equals 2, which means the z part is 2 minus the sine of t. And there is a vector-valued function, also known as a parameterization, for this intersection. Let's do a quick domain problem. What if I want to find the domain of r equals natural log of t plus 1, comma, t over root 9 minus t squared, comma, 2 to the t? I'm going to expect that you know domains from algebra. So if I consider the x part natural log of t plus 1, I know that the domain of this part is t greater than -1. And then if I look at the y part, when I have t over root 9 minus t squared, the domain of this part, that is the possible t values I can plug in, are between -3 and 3, not including the endpoints. And if I look at the z part, 2 to the t, I don't have any restrictions on the domain. So what is the domain? Well, the domain are the t values that work, and they have to work in every single part. So it's not 3 different domains, it's one domain t, because I have this one input, that works for all of these parts put together. So the overall domain would be -1 less than t less than 3. Because this part says t must be greater than -1. This part says greater than -3, but I don't care. This limits it even more. The second part says t must be less than 3, and I don't need to worry about this part over here. So this is the overall domain of our problem. So the vector-valued function is just like what we do in regular algebra. We just might have to do it 2 or 3 times, depending on how many parts, how many components of the vector that we have. Final problem. Show that the curve with parametric equations, the vector-valued function, x equals t cosine t, y equals t sine t, and z equals t, lies on the cone z squared equals x squared plus y squared. So once again, we have one input. We have 3 outputs. So we're going to have a one-dimensional curve in 3 space. So the parameterized version is not the equation. But this equation will give the shape around which my curve will wrap. So instead of drawing it, let's just do the algebra of this. And let's consider x squared plus y squared only. So x squared plus y squared is t squared cosine squared of t plus t squared times sine squared of t, which equals t squared times cosine squared plus sine squared, where cosine squared t plus sine squared t equals 1. So x squared plus y squared equals t squared. But since we state that z equals t, that means that z squared equals t squared, which we just showed to equal x squared plus y squared. And we get the result that we want.